Hello. Um, Today I'm recording this from my house. So there was a test, a midterm, last week. So hope everyone didn't mind that too much. I didn't hear great things in terms of um, the assessment. It was probably pretty difficult because it was a matter of whether you brought the correct notes or not. I'll show you. I have updated my notes because I kind of felt bad I didn't have this on my notes originally. So these 2 pages I've just added, and it's in my Google Drive. But essentially, yeah, it's just how to find the torsional constant and the warping constant for doubly symmetric I-beams, which is what was on the test, and monosymmetric I-beams, which is what has been on previous year's assessments. So yeah, I think it was about time I updated my notes to include this. Speaking of updating my notes, this week my notes on shear have changed. I'll point out where there's changes, but like it's changed a few times since I recorded the video last year, and I'll show you exactly where. So this isn't the first video I'm doing on shear. I did make a video last week or the week before, I think, and it was to do with like introducing the concept of shear. So watch that video, and it goes through how shear relates to flexure and how transverse forces on beams affect affect a beam. And yeah, so you can watch that video. I also go through in that video the web panel definitions. So that's just like if you have a beam by itself, it has an unstiffened web, so that's like an I-shaped beam. And then you can also add these stiffeners. So there's load-bearing stiffeners, which are at reactions or at the point load. But you can also choose to put in these intermediate transverse stiffeners, which just means in between where there's point loads. And then you can also choose to put these longitudinal stiffeners in as well. Yeah, and I go through that in detail in the other video. So now I want to talk about the shear stress distribution. So let me just check I'm on the right document. Yeah. So let's just say for a rectangular shape, right? So if that's a cross section of whatever material, let's just pretend it's steel. The idea is the shear stress distribution looks a little bit different to the axial force distribution. So if we have a beam in bending, right, we know that our axial force distribution looks something like this, where we've got compression on one side and tension on the other side. For shear, if you were to map this, right, the distribution on a rectangular shape actually looks like this. And this is basically rooted in solid mechanics. Actually, I recently recorded a video for my solid mechanics class going through this in detail. So if you want a little recap, feel free to check out workshop 8 on shear for Eng 2400, okay? That's on my channel. So the idea is that in order to find this shear stress distribution, right, so that's the neutral axis, right, there's a formula that you can derive where tau is a function of y, right, and that formula follows VQ over I bending in the x direction multiplied by the width, right, so that's your width. Q is you basically have to isolate, let's just say we want to find the Q, the first moment of area at the middle. We isolate just one side of it, so we're looking at that. We find the middle of that shape, right? That's your lever arm, and then you find the area of that shape, and you do the area multiplied by the lever arm, let's call it Y. And yeah, that's how you would find Q. If you want to find Q as a function of your depth, right, the idea is that let's just say, instead of finding Q exactly at the middle, your area is actually moving. So the area is actually moving. So for some variable depth like this, it's like, okay, the lever arm is going to change, the depth of that shape is going to change, etc. So you can derive a function of Q, and I go through that in more detail in my solid mechanics video. The second moment of area for a rectangle is BD cubed on 12, and then yeah, we've talked about B. V is your shear force at your point of concern. So for example, if this is our simply supported beam, and we had a point load right in the middle, our shear force distribution looks like this, and whatever value you would get for shear force, let's say it's in kilonewtons, you plug it into this formula, but it should be in newtons instead, so you multiply whatever in kilonewtons by 1,000 in order to get newtons, right? Okay, so that's kind of how that formula works. That's just the distribution function. And here's something I've updated in my notes recently. So this is kind of not written in the lecture slides, but it's written in the standards. We're specifically looking for the max shear stress and the average shear stress in the web. Okay, so how do you do that? As I mentioned, to find the maximum shear stress, right, it's going to be in the middle, basically, for symmetrical shapes, right, doubly symmetric shapes. And you would take the Q, the first moment area, as if you were considering the entire shape above the neutral axis, and you find the area and you multiply it by that lever arm, and that's how you would find it in the middle, right? I'll show you a few more shapes later, but yeah, you would find the maximum like that. For the average, you basically have to find the area and divide it by the depth. Okay, so if I was to give you a, so we're dealing with a continuous function, right? So tau is a continuous function. If I was to give you an example of a discrete function of taking the average, right? Let's say you had, I don't know, 3 people, right, and all different heights, right? How do you find the average height, right? You get the heights of 3 people, and then you divide it by 3, right? So you add them. You do the same thing if you want to find the average height of, say, a parabola, okay? But instead of like this being discrete blocks or numbers, you have to find the area of this parabola, right? And then instead of dividing by a discrete number like 3, you're dividing by the length, okay? So the idea is the area of this shape divided by the length is your average height of the shape, okay? And in our case, tau, right, we want to find the average tau, it's the average height of this parabola. That's how we would do it, okay? So you have to get the area, which is the integral, and divide it by the depth, okay? Awesome. So some more examples. Yeah, basically we say that in general for doubly symmetric eye sections, the max divided by the average of our shear stress distribution, we say it's less than 1.1, and it's, yeah, and then it's considered non-uniform shear stress. Wait, just drop something. Whatever, I'll get it later. Oh, I found it. Okay. It's considered non-uniform if it's greater than, if this ratio is greater than 1.1. You'll see in the example later. I kind of have a weird I-beam. I don't know why I did this, but basically, if you have a really fat web, right, and relatively small width of your flange, you might find that sometimes this ratio is actually greater than 1.1. But for the purposes of UBs, UCs, general sections where you have thin webs, the uniform shear stress distribution assumption holds, basically. Okay? Yeah. So the thing is, these are just definitions for you guys to understand, but you won't need to check this a lot of the time. Normally you just go, oh, I have a doubly symmetric eye section, therefore I'm gonna be considering uniform shear stress later, right? Yeah, all you need to know as an output for the moment is whether you have a uniform or non-uniform shear stress distribution. That's pretty much it. Okay, and then moving on to actually calculating capacity, shear capacity of a I-beam or whatever section you have. The formula is actually very simple, but a lot of them look similar. Like a lot of the, what do you call it? The subscripts that you're going to see look very, very similar. And so what I do in my notes is I try to color coordinate everything. So if you see different colors, you can associate the colors like as a flow chart, I guess, if that makes sense. Because I guess you'll see in a second. But you're going to see values like V, U, V, W, V, B, V, V. Because we're like, what the fuck? Why is there so many things that look so similar but they're different things, right? So I try to basically color coordinate everything. Let's just say like this. I can't remember exactly the order which I did it. Let's just say it was like this, for example. And so when you're watching this video or you look through the notes, I want you to like associate the color with a different thing, okay? And that's gonna be the best way to follow this, right? Because it's more or less just a flow chart. Okay. Yeah. Before we get on to what I just talked about, probably the quickest. There's basically a bunch of requirements you need in order to satisfy shear, right? The quickest and simplest requirement is that you need a minimum web thickness of some sort, right? So if you have a UB, right, there's a point where this web is considered too thin, right? It's like illegally thin. So that's what we're checking. And it depends on whether you have an unstiffened web or some kind of scenario with stiffening, right? So for an unstiffened web, which is just a UB by itself, for example, it needs to set, like your web thickness, right? TW needs to be greater than this formula, okay? And if that's bound by two flanges, but if it's bound by one flange, so if it's a T-beam like this, right, it follows a different equation. And then for transversely stiffened webs, right, so you basically add on these ones if you need additional, I guess, like bearing resistance, right? So this basically, I think a common theme you'll see throughout this whole topic is if you have an I-beam like this, right? If you see this shear stress distribution from earlier, you can see the majority of the shear stress actually happens in the web, right? So like we're essentially just considering the web because it absorbs so much of the shear force, right? So we're considering this, okay? And you're dealing with let's say transverse forces like this. It's essentially gonna act similar to your week 2 and 3 topic in compression for like a column in buckling, right? So remember there's two ways that a column in buckling can fail. Oh, sorry, let's just say a member in compression can fail. It can exceed its maximum squash load to the point where it reaches yielding, or it can buckle out like this, right? And so adding the stiffened web essentially helps for both cases because, well, for the case of bearing, right, aka like a locally applied shear force, no, not shear force, locally applied point load, it adds more area, right? You're gonna see this later in the bearing check, right? But basically your area is how much extra area you've just added to resist what do you call it? To resist yielding is like the area of this plate in that direction, right? So you've added extra area to resist yielding, but you've also stiffened your web against buckling like in these particular locations, right? So instead of having a column like that, you basically got, like, change it to a wall, right? Like that. So that's going to do a better job resisting buckling, basically. Okay, sorry, that was a bit of a tangent. So if you do decide to add transverse stiffeners, you basically have to follow one of three rules depending on the ratio of your spacing of the stiffeners to clear depth, right? So clear depth means the depth from flange to flange, but the closest edges of them, right? So clear just means not including the flange. So that's D1. And S is basically your clear distance between these transverse stiffeners, right? Okay. Yep, so when you have a web with a transverse stiffener, with transverse stiffeners and one longitudinal stiffener, right? You've basically braced your column, let's just say here, so it doesn't have a web. Sorry, it doesn't have a, in this particular location, it doesn't have a transverse stiffener, right? You've just braced your column right here. So now, instead of bending like a full C, you're bending it, buckling in compression. This now has to buckle in an S shape, right? Anyway, so different properties and therefore different formulas. And then sometimes you'll have two longitudinal stiffeners, say for a really, really deep kind of like bridge girder or something, for example, that you might have. And then in which case you would have, let's just say here, you'd have restraints there, and the buckling shape now looks like that, okay, in compression. Okay, so that's minimum web thickness. Next is your web shear capacity. I just draw what I was explaining a bit earlier, kind of like, in more detail here. So if that helps with your understanding, then that's good. But I like to think of how they talk about shear capacity checks in AS4100, like a flowchart, basically. Very first thing you should do is you should check for the first failure mode, right, which is your yield capacity of your web. And then you should check for the shear buckling capacity, right? I believe they're functions of each other. So you kind of need step 1 to do step 2, right? So it needs to be done in this order. And then you basically check, using those two values, you check which one governs for VU, right? So you need those two in order to get step 3, which is your shear capacity if your shape has a uniform shear stress distribution, right? So for example, if you have an I-beam, we consider that uniform shear stress distribution, right? But for example, if you have a, what's one that isn't? I think it's like a monosymmetric section. You basically don't have a uniform shear stress distribution, and so you have to basically reduce VU by some amount, right? So that's that last step there. Whereas for this type of section, VU is just VV, right? So if it's uniform shear stress distribution, step 3 becomes step 4. Okay, so that's the general overview of what we're going to do. Now to dive into the details. So, yep. So for your yield, your shear capacity yield, shear yield capacity. It's been a long day. Basically, it depends on whether it's circular or not. So, if it's circular, you follow this formula. It's actually very simple. And then this is effective area, right? And there's like a nice rule in the standards which says like if there's not too many bolts that eat up the area, then your gross area is your effective area, right? And then not only do we do that, remember we're calculating in blue step 1 you jump straight to step 4. So you don't have to do any buckling checks, right? Any shear buckling checks for like hollow sections. And the reason is, if you think about it, right, like which way is this going to buckle, right? Because for an I-beam, like it can buckle to the side, right? But essentially the pressure has like a better distribution, and like there's just like better shear flow properties for hollow sections, essentially, right? So if this is yeah, sorry, that's circular particularly, so it doesn't really buckle. But if it's non-circular, right, you have to do these formulas, including like a rectangular or square hollow section, right? And we just take the web area, so we're gonna basically ignore the flange, because the shear stress distribution looks like this, right? So we don't want to be taking any capacity from your flange because it's not going to be contributing much in shear, basically. Okay. Next is buckling. So that was like as if this was a column that was yielding in compression like that. Now we're checking if it's going to buckle out, right? So what we're going to do is we take dp, which is, oh yeah. So d1 and dp are the same thing for an unstiffened web. If you have a stiffened web with a longitudinal stiffener, these definitions change, right? So dp is your panel depth, right? So you get the panel depth and you take it as a ratio to your web thickness, right? Which makes a lot of sense because, like, let's just say you have a column, right? You would do L over let's say the width or whatever of this column. Okay, so it's like a ratio of how long it is to how thick it is. So yeah, that's just like kind of slenderness basically, right? Yeah, so yeah, this is just something you pre-calculate, and then yeah, that's pretty much it, eh? It also can't be like alpha v can't be greater than 1, right? Because your buckling capacity can't be bigger than VW. So if you have a timeline, right, this is 0 and this is VW. VW is basically like, if you remember like the flexure topic you just did, this is the equivalent of your MS. So it's like your sections, or specifically your web of your sections overall capacity. And if you remember MB, let's just say you calculated MB all the way out here, which is like the reduced buckling capacity. Like you have to set it back to what the cap was, right? Same thing goes for VB. VB is like a reduction due to buckling in your capacity, and so it can't be greater than what your original capacity was due to the web, right? Okay. Yeah, and so that was if it's unstiffened, right? But if it's stiffened, there's basically more. Sorry, like instead of just taking this formula, you should look at the table for these two values combined, and this one I'll show you in a bit as well. So for these two combined, you basically need the web panel aspect ratio, which is the spacing over the depth. So it's the ratio of this to this, or maybe it's the other way around. Sorry, it was the other way around. So S to dp. And then yeah, you need that thing, which was on the bottom of the fraction. And let's just say, that's equal to 160, and then that one's equal to 1.5. You just find the value in the table that aligns with it, right? Or you interpolate. Okay, and then alpha F is basically, what did I call it? A flange restraint factor. Okay, So it's just showing you how, sorry, it's factoring in how restrained your flanges are, right? In other words, it's like your K factor, kind of your effective length factor. So if you remember the column buckling topic, whether this was pinned or let's just say this one at the bottom was like fixed, you had a different value for your effective length factor. So this is kind of accounting for that, right? Similar. So yeah, basically the only thing that's kind of difficult to calculate here is you have to take the minimum of 3 scenarios, right? First one is this, so calculate that first. The second one has this definition, but basically it's just saying go to the middle of the web, so it's called the midplane of the web, and then measure the distance to the nearest outer edge of the flange, right? Yeah, and yeah, I've just called it y, but you can call it whatever you want. Or half the clear distance between the webs if there's 2 webs, right? And you just take the minimum of those 3 things, and that's the BFO. And then you plug it into this overall formula, it gives you alpha F, right? Okay, cool. One sec. Yep, okay, sorry. So that was VB and VW, right? So now we're up to step 3. We have the uniform shear capacity. And this is what the shear capacity would be if it's fully uniform, right? And so essentially it's one or the other, right? So step 3 is equal to step 1 if this. Otherwise, step 3. Otherwise, step 3 is equal to step 2, right? So in other words, how high is your slenderness ratio, right? If it's low, it's going to yield. If it's high, it's going to buckle. That's basically what this is. And then step 4 is what would the shear capacity be, depending on whether you need to reduce it some more due to non-uniform distribution, basically, right? So if you have uniform distribution, then step 3 is equal to step 4. Other way, step 4 is equal to step 3. Otherwise, you take step 3 and you have to reduce it by some amount. And yeah, in order to calculate these things, I've actually got an example later that I can just show you. Okay. I've talked about this in the last video a little bit, so you should definitely check that out. But this is like the interaction between shear and bending capacity. Okay. Requirement number 4 are load-bearing stiffeners. So I'm going to go a little bit quicker than I did with what I was just talking about for shear, because a lot of the time in the course there's too much content, and so some isn't assessed, right? So I'm pretty doubtful this will be assessed, but I have the notes here and just bring it into your finals in case they do assess it. It's actually pretty simple to figure out. It's pretty similar to what you just saw. So basically we're checking for bearing now, which is related to shear, but it's not the same. So before, shear force is to do with your shear force diagram, right? So here's like the shear force diagram. The value would be taking is V star, and in this particular case is equal to R star, right? So it's the same value, right? And that's what we're checking against. But for bearing checks, it's like, what are the local effects of point loads, right? So if you have a reaction or a point load, will the web basically fail in these spots, right? And if they do, then get a load-bearing stiffener and add it on, okay? Yeah, just to, I don't know, add on to this, right? If you have one point load and you've got these 2 reactions from your simply supported beam, R star is going to be P on 2, right? So these reactions, they're going to want to split your point load, right? However, if you have, let's say more point loads, right? So there's 3 point loads, and so there's even spacing, symmetrical loading. Basically, this is going to have to be 3, like all 3 of the forces that are acting down divided by 2. And this will be all of the forces divided by 2 as well. So what I'm saying is, like, check for both your reactions and your point loads, because, you know, if you have more point loads, then the reaction is going to be taking on more of that force, okay? So the idea is that point loads are never truly point loads. Like, if you think about it, right, like, let's just say, this is an example I gave in my geotech workshops, right? If you have quicksand, let's just say, and some dude is standing on the quicksand, right? At what point, like, at what scale are you looking at, right? Because if I consider this a point load, right, at a kind of macroscopic scale, and you want to, like, use that to analyze something, sure, right? You know, that'd be a reasonable kind of point load to assess. But then if I wanted to zoom in and I looked at that person's shoe on the quicksand, it's like, at what point do I start considering the area of the shoe, right? And so this is the idea of bearing. When you have bearing, you're applying a load over an area of interface between 2 things, right? So, like, for example, a point load that's acting on here, it could be, let's say, a secondary beam going onto a primary beam, right? So this is your primary beam. The secondary beam's flange area would be the bearing area, right? It's kind of the interface between these 2 things, right? So, and then if the load travels from that secondary beam into the primary beam, we basically have to spread out that point load, right? Okay, so that's kind of what we're looking at. So if we're in the middle of that beam, so let's use that for example, right? That's the depth of our primary beam along a simply supported beam. And we have a secondary beam that sits on top here. If we're around the middle, and that's, you know, that secondary beam's dragging down, or like it's got this weight associated with it, P star, let's say. The idea is that the kind of dispersed area once you reach the mid depth of the web has like 2 different gradients, right? So the first gradient, right? So let's just say that secondary beam's width, let's call that BS, right? Which I've defined as the bearing width of the top flange. When it travels through the flange, how do I say this? Yeah, you basically have to follow a certain rate, right? And then when it travels through the web to the mid depth, you have to follow a different rate. So those gradients are 1 to 2.5, and then 1 to 1. And so yeah, essentially what we're concerned about is BB, which is the net bearing width at the mid depth. So for the first case, BB is BS, right? Plus 5 TF, plus that, basically. Yeah, but you do 2 contributions of that. So just D2, right? One sec. Yes. And that gives you BB, okay? For something at the end, right, so if you've got bearing here, the idea is that you're not going to be able to utilize the entirety of either the flange or the web's ability to disperse the forces, right? And so if, like before you reach the mid depth, let's just put that even closer, like that. So it's cut off by that end distance, right? So we call that end distance BO, which is the increased bearing width contribution from the end, right? Okay. So, yeah. basically with there's gonna be, I believe, there's 6 steps here, okay, which I'm gonna call A to F, okay. The first thing you gotta do is see if your web can resist the point load without adding any stiffeners at all, right? So without LBS is load bearing stiffeners, right? And we'll check it in yielding, and then we're going to check it in buckling, right? So the first thing is yielding is this, and you're specifically checking the web's yield strength, right? Yeah. So BS is like this thing, right? The width of whatever your bearing surface is, and then you're just checking this. Okay. Next is shear buckling capacity in bearing. So basically, now we're doing a bearing check like that. We're going to do basically BB multiplied by the thickness of the web, and that's going to give you AG, right? Which is essentially, how do I say this? You basically have a wall, right, that you're checking. So a wall is a 2D column, right? So imagine you're checking a wall for some kind of, buckling check, right? The idea is that the wall can buckle out like that. So that height there, we're going to consider as D1, which you can see later. They do some like buckling check things. So that's the wall's like length basically, right? And the wall's compressive area is AG, right? Which is BB multiplied by TW. Okay. These are assumptions you make, but you basically go back to the week 2 notes, and it's literally a buckling check, right? From compression, because it's essentially that's your compressed area, right, of your web. Okay. Yeah. So the next so you've done step A and step B, which is find the yield and buckling capacity of your web in load bearing, and then step C is check if either the reaction or the point load exceeds either one of them, right? And if it does, then you need to add load bearing stiffeners, right? Okay. So if you have a load bearing stiffener, you've essentially contributed extra area, which we call AS, right? And then you also add on the yield strength of the stiffener specifically, right? Because, like, for example, these two metals could have different yield strength. So if that, let's do the web. That's the web, right? If Fy of the web is like, let's just say 360, but the stiffener is 340, you want to add them separately. So this one is Fys. Okay. Next you do the buckling check with the load bearing stiffeners as well. Very, very similar. We want to check the, it's actually a little bit different. That's the neutral axis, right, of the stiffener. Sorry, yeah, it's the stiffener's bending that way, I believe. Yep. And yeah, you want to check the radius of gyration, right? So you go like I is equal to BD cubed on 12, right? This plus this is B. The depth is TS cubed on 12. And then AG becomes this like plus sign basically. It gets pretty cooked. So instead of a wall, you have, you do have a wall, but you basically have a plus shaped wall. Like this, right? And that's your new neutral axis. Yeah. That's AG basically. Okay, you check the buckling capacity. Okay, is there anything else to say? Check if it works with the load-bearing stiffeners. Yep. And then we also want to check if the outer edge of the stiffener is continuously restrained. Which just has this check, right? Oops. Yeah, you basically, like, if you have a load-bearing stiffener and suddenly like that, it might not be continuously restrained, essentially. Wait, the width has to be less than that. Okay, I don't quite remember off the top of my head. I've never done one of these checks before because it hasn't come up in the course before. Okay. Okay, lastly I want to show you like something I did for an assignment in 2023 when the assignment had basically a check for your average shear stress to max shear stress in the web. We basically just find the function, or like the shear stress function of the web. It looks like that. To get the max, you take it from y is equal to 0, and then to get the area, you integrate it from the top of the web to the bottom of the web, getting this area of the parabola, and then you divide it by that length, right? So negative 150 to 150 is 300, which is your web depth, right? And then the section is considered uniform if that, non-uniform if that. For this particular I-beam, which has a really, really thick web and a pretty thin flange, actually the shear stress distribution was pretty parabolic, rather than, so the best case scenario is like this, where you have a more flat, basically, shear stress distribution, right? And then that will give you a uniformly distributed section. This will give you a non-uniformly distributed section. So that's what this example was in particular. Okay, so that brings me to the end of this topic, and I'll catch you guys for the bolts and welds videos.